Hi everyone, welcome back to ChemHelp ASAP. Today we are going to talk about the enthalpy of phase changes. Let's get started. So for this video, we are going to talk about three phases: solid, liquid, and gas. Yes, there are other phases, but for the purpose of this video, we are going to stick with the three most common. That gives us 6 different types of phase changes. We can have melting and freezing, we can have vaporization and condensation, and we can have sublimation and deposition. Of course, our melting freezing is a phase change between solid and liquid or liquid to solid. Vaporization condensation is either liquid to gas or gas to liquid, and sublimation deposition is either solid to gas or gas to solid. The phase changes that are endothermic are going to be melting, vaporization, and sublimation. Again, you need to put energy into the system to affect these changes. Our exothermic phase changes are going to be freezing, condensation, and deposition. You're going to need to pull energy out of the system to affect these phase changes. Now, each of these phase changes, of course, has an enthalpy associated with it. For the melting freezing phase change, we call that the delta H of fusion, or the enthalpy of fusion. For the vaporization condensation phase changes, we call that the enthalpy of vaporization. Yes, we still call it enthalpy of vaporization, even if you're undergoing a condensation. It's the same energy, it's just a different sign. And for your enthalpy of sublimation or deposition, that is going to be the enthalpy of fusion plus your heat for your temperature change plus your heat of vaporization. So let me show you these in a diagram. Okay, so this diagram here is called a heating curve. On the x-axis, we are adding heat, and on the y-axis, our temperature is increasing. So we have the solid phase down here on the lower left. As you increase the temperature, you hit the melting point. This horizontal line is your phase change. Notice the temperature does not change. This is when you are melting your solid into liquid. Once you have your liquid, you heat it all the way up to the vaporization point or the boiling point. And again, this horizontal line is your phase change going from liquid to gas. And then of course you can heat your gas up to whatever temperature you need. So my enthalpy of fusion would be used down here when I'm melting. My enthalpy of vaporization would be used when I'm going from liquid to gas. And if I wanted to know my enthalpy of sublimation, I would want to know the total heat added from when I start to melt my solid to when I'm finished vaporizing my gas. Okay, let's work some problems calculating enthalpy of phase changes. So our first problem reads, how much heat is required to melt 0.25 moles of water at 0 degrees Celsius? We are given a heat of fusion and a heat of vaporization. Now, to calculate this enthalpy of a phase change, we first need to determine if we need our heat of fusion or our heat of vaporization. So what phase change are we undergoing here? We are melting, which means we're moving from the solid to the liquid, so we're going to need to use our enthalpy of fusion. So to calculate this enthalpy of the phase change, we're going to take the number of moles times our heat of fusion. Of course, we have 0.25 moles. Our enthalpy of fusion is 6.01 kilojoules per mole. So for this phase change, we're going to need 1.5 kilojoules. Let's do another problem. Okay, this problem reads, how much heat should be removed from this system to condense 10 grams of water at 100 degrees Celsius? And again, we have our heats of fusion and our heats of vaporization. So which phase change are we undergoing? Which one do we need? Well, if we are condensing, we are going from gas to liquid, so we're going to need our heat of vaporization for that. So to calculate the enthalpy of this phase change, we're going to need the number of moles times our heat of vaporization. Of course, we weren't given number of moles, we're given grams. So we first need to calculate moles. So here's our 10 grams of water, our molar mass, and that gives us 0.555 moles of water. Now we can plug into this equation right here. So our enthalpy of this phase change is our 0.555 moles of water times 40.7 kilojoules per mole. We are going to need to remove 22.6 kilojoules of energy from the system to condense that 10 grams of water. Let's do one more problem and let's do a sublimation problem. All right, so this problem reads, how much heat is required to sublimate 15 grams of water? We're given the heat of fusion and the heat of vaporization, and we're also given the specific heat of water is 4.184 joules per gram times degrees Celsius. Okay, so you remember in the previous slide, to get a heat of sublimation, we need to calculate the heat it takes to go from starting to melt at the melting point all the way to when we have vaporized the sample at the boiling point. So these 3 steps here we need to add together. So our enthalpy of this phase change is going to be our enthalpy of fusion, again, melting our water. Then this term right here is taking the liquid and heating it up to the boiling point. And then, of course, we need to vaporize it. So we're affecting a phase change from solid to gas. We are definitely going to need to know how many moles of water we have. So let's first calculate that. So here's our 15 grams of water. Of course, using our molar mass, we have 0.833 moles of water. Now I'm going to plug my numbers into this equation right here. So here are my moles of water times my heat of fusion. That is my first term. My second term here, of course, I need to use the mass of water. That's 15 grams times the specific heat of water, which the problem gave me as 4.184 joules per gram times degrees Celsius. And my change in temperature to go from my melting point to my boiling point for water, of course, is 100 degrees Celsius. That is my second term. Now for my final term, I'm using my heat of vaporization. Again, I'm using my number of moles of water, my 0.833, times my heat of vaporization, which is 40.7 kilojoules per mole. Okay, so let's simplify these numbers just a little bit. When I calculate my first term, I get 5 kilojoules. My second term gives me 6,276 joules. And my third term gives me 33.9 kilojoules. I have a little bit of a problem here. I can't just add these numbers together. Why not? Because I have this second term is in joules and the first and third term are in kilojoules. Remember, when you are adding numbers together, your units must match. So the first thing that I need to do before I add these together is convert this joules into kilojoules. Okay, so here's everything in kilojoules. Now I'm ready to add everything together. And it's going to take 45.2 kilojoules of energy to sublimate that 15 grams of water. It's helpful for these longer problems to at least sketch out your either heating or cooling curve and get an idea of what point you're going to start at and what point you want to end. I hope you found this video helpful, and thanks so much for watching.